Today, I'm pleased to introduce today's session, Effective RAG at Scale, the role of vector embeddings, and our guest speaker, Atindriyo Sanyal. Welcome, Atin. So I'm going to kick off this presentation, and Atin and I will give some commentary along the way, and towards maybe halfway, 2/3 in, I'm going to hand it over to Atin to talk about evaluation for retrieval augmented generation. So first, I'll start off with a little bit about me. My name is Yujian Tang. I am the developer advocate here at Zilliz. I have a QR code there on the side that if you would like, you can scan the QR code that will take you to my LinkedIn, and we can connect and you can ask any questions you would like there. My background is mostly in machine learning and software engineering. And for the past few months, basically all I've been doing is building RAG apps. Atin, would you like to introduce yourself?
Yes, thank you for having me here at the webinar today, and thanks everyone for joining. My name is Atin, and I'm one of the founders of a machine learning company called Galileo. And we're essentially in the business of evaluating models better and providing better frameworks for evaluating, particularly unstructured data related models and use cases. And RAG is certainly a very big part of that entire use case. A bit about me. I spent about 12 odd years now in specifically just building machine learning systems, mostly for slightly larger companies like Apple and Uber. Spent the earlier part of the last decade for many years at Apple, doing like old school NLP. Mostly a lot of the ML tech we built went into Siri and eventually a lot of other Apple's AI ecosystems. Funny enough, I was part of the first effort we had towards building APIs for NLP, which was at Apple, we called it Siri Kit, which was the first Siri API. And it's funny to think that was started in 2014, almost 10 years ago at this point, and there's so many parallels I can draw towards new age LLM workflows like RAG workflows, albeit the issue was back then that models weren't as powerful as they are today. I also spent many years at Uber, was the architect of the first feature store, which was built at Uber's Michelangelo team, and did a lot of work around basically figuring out data quality for all of Uber's machine learning. And a lot of those learnings went into founding Galileo with the principle that evaluating models is certainly a big challenge and there's a lack of tooling around evaluating models better. Yeah, thank you for having me, and hope you find this webinar interesting.
Yes, and for those of you who haven't scanned the QR code there, that is Atin's LinkedIn, if you would like to go find him on LinkedIn. So today we're going to cover essentially these 5 topics, or really 4 topics in a demo. We're going to talk about why would you use retrieval augmented generation. Then we're going to talk about how you can build your RAG apps. And then we're going to talk about the role of vector embeddings. We're going to kind of look at what they are, how you get them, what they do, and then evaluating your RAG outputs using vector embeddings. And then at the end, we're going to go into a demo. Atin's going to show us how you can use Galileo to evaluate your RAG outputs. So we'll get started with why use RAG. So the real thing that we look to tackle with retrieval augmented generation is that large language models don't have access to your data, but not only that, a lot of them have the tendency to hallucinate. And here I've just picked a couple images to kind of demonstrate this, right? So a lawyer used ChatGPT in court sometime within the last few months and cited fake cases and got in trouble for that. And, you really don't want to be that guy. You really don't want to be that lawyer. And in addition, there was a lot of buzz in academia. There was a lot of buzz in schools around people using ChatGPT and making up like fake articles to cite and to talk about. And I believe that you also have something cool to say about this hallucination stuff as well.
Yeah, I mean, I've been deep into hallucinations and figuring them out for modern LLMs for the last many months here at Galileo. And first off, of course, RAG is probably the first antidote to hallucinations simply because LLMs are frozen in time. And how do you solve that problem? How do you bring them to modern day reality is through RAG. But there's at a higher level, there's many dimensions to hallucinations, and RAG is sort of designed to solve this one key aspect where every LLM response that you generate needs to be grounded in some very specific context, and that's the context that vector DBs and RAG workflows provide. But it gets interesting when you talk about like the other dimensions of hallucinations, because there's intrinsic hallucinations which are more closed domain, but there's other extrinsic hallucinations which are like factual errors which these kind of models make. And there's a lot of very interesting techniques which I'll share later on how to detect those. But the embeddings and the role of a vector DB is extremely important in fetching the right context, and that's probably the 0 to 70% mitigation strategy for hallucinations. Yeah.
Yes, and that's why we promote using Milvus to solve this problem. So let's dive into why LLMs hallucinate, and then we'll kind of get into how we're going to solve this issue. So I'm going to take you guys all the way back to the maybe 1970s when neural networks were coming out, right? So we had these perceptron things come out in the late 50s, early 60s, where essentially what they were doing was learning some sort of data. And what we found was, hey, if you put a bunch of these perceptrons or neurons together, you can actually get something that models a more complex relationship, more complex pattern in your data. And so when we started doing this, we did this with initially just one of these neurons, right? It just takes an input, and then there's some sort of bias, it does some sort of math, and then it gives you an output. As we moved and we started putting these together, we've come up with this neural network structure where we've started arranging these perceptrons and these neurons in layers. And this image here is a very basic neural network that shows you a 3-layer deep neural network. And the reason why it's called deep is because we have a hidden layer in here. And this hidden layer is going to come into play as an important piece of working with vector embeddings later on. We'll cover that in a later section, but do remember that the hidden layer is an important piece of this vector embedding workflow. So from here, we moved into recurrent neural networks for natural language processing anyway. So what we actually found is that certain neural network architectures are better for certain kinds of data. So the basic neural network architecture that I showed before, that is good for basic kinds of data. Maybe we have a bunch of numbers and we're trying to find some sort of classification. There's two kinds of neural networks that became popular for working with data that wasn't naturally easy to kind of insert. And those were convolutional neural networks and recurrent neural networks. So for natural language processing, we found that recurrent neural networks were a great architecture because what they allow you to do is take sequence context into consideration. So you'll see here, this diagram, don't worry too much about the diagram and understanding it. What you should pay attention to in this diagram is this ht minus 1, xt minus 1, ht, xt, ht plus 1, xt plus 1 thing, right? So these three little blocks here essentially are showing you that when we do a recurrent neural network where we feed back the output of some of the neurons back into themselves, we get the ability to keep track of these tokens over time, this context, these sequences over time, right? So for example, if we had like a sentence such as the cat in the hat, we could see that, maybe we're at the word cat, and we'll see that xt minus 1 is the, xt is cat, and xt plus 1 is the cat in. And then, as we move along, we'll have different words at xt, but everything else around it remains in the same concept. One of the problems with recurrent neural networks is that over time they lose context, and they lose context for many reasons, but perhaps the most well-known reason is the vanishing gradient, which the vanishing gradient problem is that as you do more of these operations, your change or your gradient kind of becomes zero, and then you no longer have that information. So the way we got about this was to build something called a transformer architecture. And what I have on the screen here is like a super simplified example of what a transformer architecture looks like. But at the base, transformer architectures take an encoder, and they use the encoder to take your input and transform it into a hidden state. And the hidden state is really just a bunch of vectors or, like a matrix. And the hidden state encodes the context of your sentence or your sequence over time, as well as the current positional embedding of where your token is. Then we feed this set of vectors, this matrix, into a decoder, and the decoder may or may not apply something called self-attention, which I have marked here as additional input, but you've probably heard the term self-attention before. And so the decoder may or may not apply that. Most of the times, in most architectures right now, it does apply self-attention. So you take the hidden state, which is a matrix, you take self-attention, which is also a matrix, and then you feed them into the decoder, and the decoder gives you, hey, here's what the next token should be, or something like that. And actually, that's exactly what GPT does, right? So GPT is a decoder-only architecture. So when you feed GPT words, it actually turns this into tokens and positional embeddings, which gives the decoder the hidden state or the the information that it needs to put out the next token. And so in this example, you can see that when we give GPT, the chicken walked, it should produce something like across the road, because this is something that it may see commonly. Probably this is what we expect to see the most commonly in its data, right? So what it's really doing is it's predicting this next token. So when you see the chicken walk, it's predicting across, and it's saying that, hey, across is the most probabilistically most likely token that's going to come up next. So that's what we're going to put out. So so the reason ChatGPT hallucinates is because it's set up to predict a series of words or tokens. Now let's go into how you can build your RAG app. So essentially, RAG is injecting your custom data on top of an LLM and using similarity search to find the right data. And this works really well for one of the types of hallucinations that Atin mentioned earlier. Atin, did you want to expand a little bit about the other types of hallucinations as well?
Yeah, no, for sure. So yeah, it's a good sort of premise to what we're getting into here. Because one of the key purposes of RAG is to bake in context into the LLM responses. But just super high level, we've done very interesting experiments internally on just measuring and quantifying hallucinations in modern state-of-the-art LLMs. And we consider anything that's GPT 3.5 and beyond as something that's state-of-the-art. A lot of our evaluation philosophy and metrics don't really cater to some of the older GPT architectures, because the modern ones simply don't make those simple mistakes anymore. Yeah, it's very interesting, some of the revelations that we've had from our hallucination experiments, one of them being in context of RAG, there's this idea of how much your context or your documents are grounded, or how much is the output of the LLM grounded in the context that you've provided, which is, of course, obvious. But then the next level of challenge in these kind of workflows becomes how do you specifically point to the areas where which the model used to make that assertion or that answer, because a lot of the errors are a little more abstract it's more reasoning based, and it's hard to pinpoint specific tokens. So that's where, the next level of challenge is figuring out how do you bake in more explainability into the whys, whether, the answer is grounded in the context or not. How do you take it a step beyond? So that's in context of RAG. There's more open domain use cases where you typically would answer something that's, that you're essentially trained on without using the context. And in those cases, I think the hallucinations typically tend to be more around logical or reasoning based errors or factual mistakes. So those are essentially the 2 or 3 dimensions of hallucination. And I'll talk a little bit more about in my slides about the key inputs and outputs to an LLM system, particularly an RAG system, and then we'll go deeper into what specific kinds of errors occur in the input, in the context, and the output that leads to hallucinations. But I'll let you continue here.
Okay, cool. Yeah, I mean, I'm excited to hear about that in the later sessions. So let's start off with what a basic RAG architecture kind of looks like. So essentially what you're doing when you're building a RAG architecture is you're thinking like, okay, how do I inject my data on top of this LLM, right? And so actually what happens is, well, you can actually drop this first LLM thing, but this is most of the times I see people use an LLM to make their query more like queryable and searchable semantically in the vector database. But typically what happens is you as the user, you got a query, you come in, you say, hey, I want to know like what animal is in a hat. And it goes to the LLM and the LLM says, oh, find me, animal hat. And then it goes to Milvus and Milvus says, oh, the cat in the hat. And then it sends it back to the LLM and the LLM takes that and says, oh, okay, well, this is the semantically the most similar response that we have in the vector database. We're going to make that human readable for you. And we're going to tell you the animal that's in the hat is the cat, right? So that's the basic RAG architecture of just saying, query, break my query down into something that makes sense, ask my vector database like Milvus, what's the most similar thing you have? And then we get it back and we say, okay, now let's match that back to our original query and answer the question. So that's the basic one. And then if we move on to, oh, I didn't add that in here. So the basic tech stack for RAG, actually, you know what? I'm going to pause here because there's also a couple things I wanted to add here. You can make this architecture better, actually, by inserting a caching layer. Of course, this is under the assumption that you're going to have a lot of use for your RAG app. And this is actually something that we saw internally when we built OSS Chat, was that a lot of people were asking very similar questions. So OSS Chat, I don't believe is in this slide. Yes, OSS Chat is not in the slide deck, but osschat.io is a site you can go to ask about open source software. And we built this and we found that, hey, a lot of people are asking very similar questions. Maybe we can cache the questions and the responses, and not only will the user get a faster, better experience, but we're also going to save money by not calling OpenAI's LLM API endpoint all the time. So that was something that we found that, that sits right here. Basically, before the query goes to the LLM or Milvus or anything, we're going to send it to the cache and see if we have an answer. So the basic RAG tech stack looks like this, right? You have ChatGPT or any other LLM, right? Llama, Falcon, whatever. And then you have a vector database, and you have some sort of framework, some sort of prompt as code framework. And the way that you can think of this is like a computer. So in your computer, you have a processor, a CPU, something that allows the computer to perform a bunch of operations. And then you also have ROM, your hard drive, right? And that is what allows the computer to store its memory. And that's where Milvus is. And then you have something that allows you to interact between all of these different components, as well as allows you to interact with the computer. And that's where Haystack or LangChain or some other prompt as code orchestration framework comes in. And the reason why this architecture looks this way is because one of the core driving factors of being able to do retrieval augmented generation is being able to do this similarity search, this semantic similarity search, right? This is essentially what the vector database provides as a functionality. So what happens in similarity search is you come with your data. It can be any sort of unstructured data. It can be images, videos, audio, PDF, CSV, whatever. As long as you have the right vector embedding model, and that's the step from 1 to 2 here. As long as you have the right vector embedding model, you can embed any kinds of data into a vector, and then you store it into a vector database. Then at query time, when it's time to ask questions, when it's time to do product recommendations, something like that, in terms of RAG, when it's time to ask questions, you once again take whatever data it is that you are going to ask questions about. Maybe you have an image that you want to turn into a sentence. Maybe you just have a sentence you want to ask a question. And you use the same model that you used before to get the vector embedding. And this is very important, that you either use the same model or at least ones with the same dimensions, depending on what you're measuring, because vector similarity can actually, it only makes sense to be done on vectors of the same dimension. So this is an important step. You want to make sure you're using the same model. Once you have those vectors, then you feed that vector into the vector database, and the vector database performs an approximate nearest neighbor search. And this is essentially the similarity search. And we'll cover kind of what that looks like in the next section. What I want you to get out of this this slide is essentially, what are the steps? What's the workflow that's happening here, right? So once you have the vectors that are your approximate nearest neighbors, you get those results, and then the LLM will once again, turn those results into something human readable and send it back to you. So the takeaway from this is really that a RAG app can be built like a computer. You use an LLM for your compute. This is your CPU, your GPU, and a vector database for storage. So that's your hard drive, your solid state drive, and your prompt as code, which is the interface. How do things talk to each other? Right. So this is the main takeaway. LLM, vector database, some sort of prompting. So what are the role of vector embeddings when it comes to RAG? This is going to be a short section. This is going to be the last section that I cover, and then I'm going to pass it on to Atin to cover evaluation.
Actually, Yujian,
Yes.
if you can just go back to the slide before this, I just want to highlight something interesting for our audience here.
Yes.
So the first part, the left-hand side of this diagram, is very interesting and very important because it kind of takes me back to some of the more complex embedding generation techniques that I've worked on in the past in my career, particularly for recommendation systems, where we, for example, instead of just using sentence transformers to create embeddings and store them in vector store, there's more complex model architectures where you, like the two-tower architecture, where you can essentially take user embeddings and item embeddings, say for a shopping website. In our case, in my own experience, we built the entire vector search ecosystem for Uber Eats, and there we would create embeddings from user activity on the Uber app. In fact, there's a paper that workshop paper we wrote with folks at Stanford that I wrote. If you just Google feature stores for embeddings, hopefully that should pop up. But what that does is it specifically talks about how there's certain sets of embeddings which are dynamic in nature, and they change over time as you interact with a system. Say,
Yeah.
in the case of a shopping app, you're using the app and you're generating clicks and you're dynamically evolving embeddings. So the left-hand side of this diagram sort of highlights this a more complex workflow where you have an embedding management system which is constantly curating newer embeddings for users, and which eventually get stored in a vector store. But there's some very interesting new RAG use cases which are coming up from my discussions with many of our customers and even beyond, where you want to use these kind of embeddings, which are not necessarily text embeddings, but then you tie that in with a multimodal model to generate textual representations of user activity, which eventually gets stored in a different index in the vector store, and that serves as input to an LLM. That leads to a more complex workflow, but that can solve some very interesting problems where you're essentially textualizing user activity. I know a few friends of mine who are building Zipline, which is Airbnb's feature store. They're exploring these kind of ideas where you essentially create textual representations of user activities and then use a vector store to augment the context of an LLM, and then you can generate very interesting analytics and summaries of user activities. And just a very interesting new use case which is coming up, and I see that the sky is the limit for RAG workflows. And this is just an example of that.
Oh, okay. That's really cool. I hadn't heard about that. So I'm actually going to just ask you to dig a little bit more into that right now. So for the transform side, for the left side, you're saying that there are ways where people are working on, or maybe there already exist methods where you're taking like a live thing, what's going on in the app, like some sort of, I don't know, is this like some sort of like features of what's going on, and then they're transforming that into the vectors to store, and then when it comes to query time, they're able to do that again for the same user, or what's going on when it comes to query time?
Yeah, no, absolutely. So essentially, there's established architectures like the two-tower architecture, which many of the audience might know. But you should certainly read about the two-tower architecture, where you essentially take features from say users, from items, from any entity that's in your data warehouse, and then you create vector representations from those features. And the vector itself is the output of a two-tower deep learning model. But that has proven to be a very efficient way of representing more abstract things like user activities. And you can cluster people who are interacting with your system the same way into a cluster because those embeddings kind of map up in the same space. But leveraging those into a language model is this new avenue of RAG workflows, which is sort of emerging now.
Wow. Okay, that's really cool. I haven't read this paper, so I'm gonna go check it out.
Yeah. Yeah, just Google feature stores for embeddings, and that should come up. It's an old paper, but it was essentially, we wrote it seeing this upcoming wave of just vector databases being a lot more important because of the importance of embeddings and some of the problems that we were able to solve a few years ago. But it was interesting how, with the advent of GPT and LLMs, how it's manifested is very interesting.
Yeah. Okay. So I'm going to talk briefly about the role of vector embeddings and how you can get them other than using the twin tower method, the two tower method. And then I'm going to pass it on to talk about eval. So traditionally, most cases, vectors come from some sort of deep learning model. Essentially, you take your knowledge base. This can be, as I was saying earlier, images, videos, text, audio, whatever you need, and you feed it into a deep learning model. And in the case of deep learning models like ResNet or sentence transformers, like mini LM, what you do to get the embedding is actually you just cut off the last layer. And then you say, what are the outputs? And that is the vector embedding. And these outputs are the internal semantic / numerical representation of this input from the model. And then once you have those vectors, you store it into a vector database such as Zilliz or Milvus. So before we get into how do you evaluate this kind of stuff, I just want to leave you with this quick kind of like tutorial summary, basic commentary on how semantic similarity works with vectors. And the basic idea from this slide that I want you to get is that you can do math on words or images or anything other than things that are originally numbers using vector embeddings. I also want to point out that, you will never see two-dimensional vectors in real life, and you will never see anybody doing Manhattan distance as their vector metric in real life. But this is a toy example to get across the concept, so let's get into it. So What I want to show you here is the word queen, 0.3, 0.9, minus the word woman, 0.3, 0.4. In addition, it gives you, this 0, 0.5. And then if you add the word man, 0.5, 0.2, you arrive at the 0.5, 0.7, which corresponds to king. And a couple other things I want to note here is that it's important to see that, hey, look, queen and woman have the same value on that first dimension. And what that tells us is that these words mean the same thing along that first dimension, but it doesn't tell us what that dimension means. It doesn't tell us anything about what the dimension means. It could be that both of these words have 5 letters, and that's why they have the same value along this dimension. It does not necessarily tell us what that dimension means. It just means they have the same value along that dimension. The other thing I want to point out is that queen and king and woman and man differ by the same values along the x and y axes. And what that means is that these words have the same relationships along that dimension. Whatever the transformation is that applies is the same from queen to king as woman to man. So that's basically what I wanted to point out. And I just want you to get the idea that, hey, I can do math on things that aren't originally numbers via vector embeddings. And now, I'm going to turn it over to you, and I'm going to stop sharing my screen, and you can share your screen.
Sounds good. All right. So in this section, I'll try to cover something which is very, I guess we consider as a company very, very important in as a practice in any machine learning workflow, which is evaluation. And the whole basis of founding Galileo was that we need better evaluation metrics and traditional metrics that we use for accuracy measurement, etc. They're necessary, but they're not sufficient. They treat all kinds of errors the same way, and they're unable to distinguish the big errors from the bad, and as well as the fact that a lot of the errors essentially boils down to the data. We are basically in the business of creating new sort of metrics for modern sort of ML workflows. And the LLM workflow, the RAG workflow, the VectorDB workflow is this new workflow which has emerged. So I'm going to talk about how do you evaluate your general health of your RAG workflow and what specific parts do you should look at. So keeping it super high level, just to just bake in the understanding of the importance of this and what to truly evaluate. This is a 10,000-foot view of an RAG workflow. Here you can see that on the left-hand side, you have the prompt or the query. Of course, on the right-hand side, there's the output of the LLM, and the gap that VectorDBs are filling is essentially baking in context and baking in very relevant and similar context to what you need. And of course, you can achieve that at scale using technology like Zilliz and Milvus. But there's a lot of questions which prop up in this workflow. And these are essentially unknowns to the practitioner. And typically the questions which are asked are, on the prompt side, whether your prompt is pertinent to get your desired LLM outcome. On the documents or the context side, which is the data that's fetched from your vector store, are the documents relevant? Are the documents fetched from a sparse space in the embedding space? Are these documents relevant to the and most ideal to get the desired outcome? Because in the end, whether you're an application developer or a model fine-tuner, you're trying to get the best output from your model. And there's all these knobs that you can tune to tune the output of the LLM. So it becomes very necessary to quantify some of these issues that you're seeing. On the output side, of course, there's the big issue of hallucinations, which in the context of retrieval augmented workflows essentially boils down to how much of the context your model used to answer the query, and which parts of the document was the answer sort of grounded in. So what we've done is we've calibrated and quantified some of these issues into metrics. And I'm going to talk about some of these, and I'll also demo a few of these metrics in a very simplistic RAG workflow. But just talking through them, on the prompting side, there's prompt relevance, which is a quantification of the pertinence of the prompt or the query to the output of the LLM. On the document side, there's I talked about sparsity, just diving a little bit deeper into sparsity, why that can be an issue. Your vector store essentially stores the embeddings of the entire set of documents, which you can consider the syllabus or of your LLM. And of course, these vectors are embeddings, which are derived representations of the original documents. But as Yujian had mentioned, the cool thing about embeddings is that you can do the math with it, and they kind of cluster together very, they give you insights into raw data, which you wouldn't have otherwise gotten. But a typical operation with embeddings is, of course, dimensionality reduction and clustering, and they kind of map into this n-dimensional space. But the space can be dense, it can be sparse, depending on the overall set of documents that you put into your vector DB. And the sparseness and the density of the regions from which you fetch your context and your documents can make a big difference in the output of the LLM. So sparsity is essentially just a measure of how dense or sparse is the region of the embeddings that you fetched your data from. Then beyond that, there's the relevance of the document, like which I was talking about attribution and actionability earlier. Like it's one thing to quantify something as good or bad, but how do you take the next step? And in case of RAG workflows is the fact that if you detect an error in your or if you detect a hallucination or an error in your output, the goal, like the first step is to sort of quantify the error as how high level, how grounded was the output in your documents. But then more specifically, which areas of the documents that the model consider towards the answer. So doc relevance is a metric that is sort of a measure of that quantification of that. And then finally, the main one is the output of the LLM, whether it hallucinated or not, which we talk about through a metric called, we call it groundedness for now. It's a fairly simplistic metric, but the technique that we use to measure, this is Galileo's groundedness, and we use a very nuanced chain of thought to be able to reason about why something might be grounded in the documents or versus why not. And we found that to be a very effective technique. In fact, just a quick highlight of a lot of the hallucination work that we've done for the last many months. Essentially, we've curated over 15 data sets across many kinds of different LLM tasks, and had experts from the world over go through thousands and thousands of data points and label them as hallucinated or not. And these were domain experts. And from our experiments, we've done a determination of groundedness through this chain of thought method that I was talking about. It showed over an 85% AUC score, which is an 85% accuracy and match with these human annotated hallucination experts. So I'm just going to touch upon that a little bit in the demo as well, but just wanted to highlight that. So tying it back to the original workflow that you saw, I think the missing piece is essentially just this algorithmic evaluation and quantification. And it's a loop, right? Like you figure something out, then you go back to your querying and you adjust the query, you adjust the documents, and you keep doing that till you fine tune yourself into the ideal output of the model. So just adding a few components to the simplistic workflow that we saw for RAG. All right, enough talk. I'd love to get into a demo, and just keeping a check on time here.
Good. It's 9:40, so you should have should totally be good.
Awesome. Great. So in the demo, just to give some high-level context, it's a fairly simple demo just to convey the idea, but feel free to use your imagination to apply the same principles to more complex RAG workflows. But in this demo, imagine that you are a data scientist that's building a Q&A system, and your goal is to build this question and answering machine, which purely answers based on the documents which are provided as part of your input and not rely on any extrinsic information. So you have this LLM in the loop, which is this pre-trained model or some API, which is backed by a very, very powerful GPT 3.5 or 4 level model. And you're trying to construct this RAG workflow, which tries to restrict the output of the model purely to the documents that you provide. It could be for various reasons. You work for a fintech company or a healthcare company where you're not allowed to divulge general information and things of that sort. But I'm a data scientist or a prompt engineer who's building this LLM app. I'm going to use a Milvus. So the first thing I'll do is I'll install a bunch of libraries, including PyMilvus here. And once I do that, I'm going to set my environment variables here. Just getting to the main components. Here you can see that one of my goals is to generate embeddings for the original data or the documents that I have. So in this case, I'm using a sentence transformer, which is a simple sort of BERT-based embedding that you can very easily generate through one line of Hugging Face code. And I use that transformer model to generate embeddings for my documents. Here, I'm initializing my Milvus vector store. And this particular piece of code is to essentially, it takes the query, which is the input to the RAG system as the input. And then it, of course, we use our nsimilar method that Milvus offers. And then we sort of, we take those embeddings, and then here in the demo, you can see that we are essentially concatenating that into a simplistic data frame. So the data frame here contains the input questions like, explain vector embeddings. What is the best phone to buy? What is machine learning? So it's a Q&A system. So this is the original input. There's the textual context, the actual document chunk, the embedding for the same, which was fetched from the vector store, and the embedding of the query, which was generated from the sentence transformer. So I club all of that into a simple data frame. Now, because I'm doing prompting, I'm going to define my prompt. And here, this is one example of a prompt. Typically in my experimentation phase, I'll be trying out many different tweaks and turns into the prompt, mostly based on the evaluation metrics that I'll show you. But here's an example of one prompt, right? Like you essentially say, you tell the model that you're an expert Q&A person, but you only want to answer only based on the context below, and don't directly reference anything that's outside of the context, and but also kind of avoid statements like based on the context. So you're steering the model here through the prompt, but essentially you're providing this context. In Galileo, we use context as a keyword to detect the presence of RAG and sort of calibrate certain RAG specific metrics for you. I'll just show you that in the second. But you can also override in Galileo using the Python library the specific metrics that you are interested in. So say you're only interested in groundedness and context relevance, you provide that. Of course, you can, there's a whole host of other metrics which should show, I think what's this? The notebook is not connected. That's why it's not showing, but there's a whole host of metrics that you should see in our scorers library. So in this case, I'm overriding the general metrics calibrations to mainly give me these two for the RAG workflow. There's certain metrics which are automatically included. If you have ground truth, if you have baselines, we give you the usual suspects to you. Uncertainty is another interesting metric which we have in our system. It basically measures the confusion of the LLM in its own output. And the way we do that is we track entropy in the tokens that it's spitting out. And that gives you a good sense of where the model wasn't sure and where it was certainly sure. And through our experiments, one interesting thing that we've seen with these modern, these machines is that they're often, when they start speaking, when they start spewing out the initial set of tokens, they're often very high on entropy because they're kind of almost like warming up. And then as they start speaking, or as they start spewing more tokens based on the attention that they've already sort of accumulated, the entropy sort of gradually goes down. So it's very interesting to see the internal behaviors of these models. But that's also another score that we give you, and that gives you a good sense of the confusion in the output. All right. Once you define the metrics and the template, you just log into, you use pq.login. PQ stands for prompt quality, which is our Python library. So you just pip install prompt quality, import prompt quality as PQ, and then you can do this. You can log into your hosted Galileo environment, just one line of code, and then one more line of code to run your RAG workflow. And here in our case, we're specifying the project, the template, which I just curated, the data frame, which had the context from the vector store, as well as the set of metrics that I'm interested in, as well as the model that I want to query. So this is basically your experimental line of code, right? Like to define your experiment. And this is just a single experiment. We, of course, allow you to do what we call sweeps, which allows to take vectors of or arrays of models, arrays of hyperparameters, and we do some interesting sort of optimizations behind the scenes and run a batch of runs. So here, I'll just get into once you run this, you'll get this output. It'll do the entire, execute the workflow, and it'll give you this link to go to, which I'll go in a second. But you can see we also give you the data, like the object itself, the prompt metrics Python object. So you can, which has your hallucination number, like what was the quantification of hallucination and other stuff like latency and cost. So you can literally build an entire system using just Python. Like you can build an entire observability system because you get all these metrics out of the box. Before I go into the demo itself or the console, just want to highlight an interesting extension to this experimental framework that we're working on. So typically in experiments, I was talking about using different templates, different kinds of inputs and tweaking the prompt to get better output. But in the RAG workflow, you can also leverage different embeddings. Vector DBs allow you to store different indexes where you can store different sets of embeddings. So here, what we want to do is we want to give you a layer of experimentation on top of the vector store where you can essentially fetch multiple embeddings. You can generate one with a sentence transformer and another with a two-tower model, and you want to see which ones work better. So we are working on a new version of our API, which allows you to override these transformation methods where you can specify one or even more than one way of generating the embeddings, and then you sort of stitch together. You provide the transform, like these functions here, and then behind the scenes, we will do this A/B experimentation and give you, which one hallucinated more or which ones led to less hallucination and so on and so forth. So yeah, just wanted to bake in this idea that through just Python code, you can run these very advanced experiments using a vector DB. But once you run this, you click this link, which leads you to here. And this is the Galileo UI, of course. And there's at the high level, this is the one run you did. And if I go back to my data frame, the single run is testing out 3 queries, right? There's the explanation for vector embeddings. What is the best phone to buy? Those are the things that I'm testing with. So if I click into this, it will show me those 3 queries that I made, and it'll show me the stitched together version of the whole thing. So already off the bat, what you want to do is when you start your evaluation process, you look at these top level metrics. And already one thing you see is that there's the aggregate uncertainty is a bit on the red. It's a bit on the higher side. It's 0.36 might sound low, but we use standard deviations. So red means bad. But also I see that the context relevance, which is an RAG metric, which I was interested in, it's kind of on the lower side. There's something off. Ideally, I would expect it to be between 0.9 and 1. And here I can see at the last column, if you see, if I, here you can see that there is one of the requests was clearly not, there was some grounding issues with that. There's a culprit here, which has slightly lower relevance. So I can click into this and I have a host of metrics to evaluate out of the box. The main one that I want to highlight is the groundedness metric, which is using, as I said, like it's using chain of thought at to figure out whether the model itself can tell whether its answer was grounded or not. Because one of the realizations that we've had from our experiments is these models are often very not as good as not making the error in the first place as they are good at realizing that they've made an error. So there's many ways to, there's tricks that you can do with prompting to make the model realize its own mistake. I'll give you, this is a very interesting example. So let's look at the input here. You're an expert Q&A system. Oh, I already went through this. The question that I'm asking here is, what is the best phone to buy? And the context information, which was fetched from the vector store, was it said the advantages of Moto, MobileNet. The model is great for a few reasons. It's some random text which was fetched from the vector DB in this case, where clearly you see that the model would struggle to answer this kind of a question, what is the best phone to buy? And here you see the output of the LLM was MobileNet, which to the human reader, you see it's not really the answer if you think about it. Like it's just saying the advantages of Moto is MobileNet. That's not really the best phone to buy. So with groundedness, we automated that reasoning. So here it says 0, which is negative. And if you hover over it, it gives you the reason that the best phone to buy, the response was MobileNet. However, there's no information provided in the context that directly supports this claim. It only mentions the advantages of and disadvantages of Moto. It does not compare any specific phones, and the response is not supported by the documents. So this was our RAG metric groundedness at work here, and we automated that. And doing this at scale, imagine how much more leverage you can get in your evaluations. Even beyond that, just want to highlight certain other things like you get LLM uncertainty out of the box. In this case, you can see, as I had told you before, the model started off being a bit uncertain, just like they usually do. But the funny thing was that the answer itself, when it said MobileNet, it was very confident. So it made a very overconfidently wrong answer, but we got it to admit its own mistake, if you will, and were able to figure out that the answer was wrong. So this is essentially, just evaluating a single workflow. There's, of course, a lot more you can do. If you have, say, multiple runs, there's many ways to sort of, compare. If you had multiple runs, you could hit compare runs, and it would load it in this columnar view where you can, essentially enable these things, and you can look at these responses, and it's a very easy way to do A/B evaluations. And at the end of it, once you decide on the winning run, in this case there's just one, Galileo gave this one as the winning, you choose this, and then you write, you click here, and then you can essentially get the entire code for that workflow and copy it and paste it into your Python environment, and it'll just run it programmatically. So super, this sort of blitzkrieg sort of a demo. There's, of course, a lot more here. And but this is how you can do like rapid experimentation and very precise evaluation of modern LLMs and modern prompt workflows and modern RAG workflows with Galileo. I'll hand it back to you, Yujian.
Awesome, dude. Yeah, thanks for going into that. That was really cool to kind of hear about. It seems that we have a lot of questions. This is great. We don't we only have a few minutes. I don't think we have time to address all these questions. So what I'm gonna do is I'm gonna try to address some of these QA questions that are here in the QA, and then I know that a lot of you guys have sent questions in the chat. What we can do is, if you have any of these questions that you want answered, you can simply, we'll put the video up. It'll go on YouTube. You can ask on YouTube. It'll be on LinkedIn. You can message us. You can make a post and tag us, ask us, whatever. But we won't be able to get to everything, so I'm going to shut up and try to get to the questions now. So number one is, isn't a focus on hallucination misguided? Isn't the more important issue the need to include private confidential information into the NLP application? I think this one's for me. I'm gonna say, is the focus misguided? I don't know. Could be, but yes, the importance of RAG is that it allows you to provide this private confidential information. And there are some nuances here, but you can also use this to, stop the LLM from making up answers. And that's the hallucination part, right? And so there's a little bit of both here. And then, if the local knowledge base has all information of interest, what is the advantage of including it in the query and sending it out to a foundation model? Typically, we want to kind of combine multiple answers, multiple things that you get back. And then we also want to make sure that it's human readable. So the point of getting the answers from the vector database and then using the LLM to mess with it is so that it actually answers your question. How do you cache when questions can be worded differently? As long as the vector embedding is within a certain distance, and that is up to you as the implementer to decide, you can say, hey, this is close enough, we're going to return this answer. Is NLP using RNN now considered obsolete and replaced by LLMs? I mean, maybe not entirely, but pretty much from what I've seen, yeah.
Yeah, I mean, that's certainly a trend that we are observing in the industry, where people are trying to build more practical systems with these LLMs, the modern LLMs. There's no question that these architectures and these newer LLMs are way better, to the point where metrics and papers published even as early as 2021, they no longer apply. These models are just incapable of making those basic mistakes. But that said, what's still to be figured out is, how do you build practical systems with these LLMs at scale? But the buck is certainly moving in that direction.
Yes, same from here. Slide 25, does the RAG box include the LLM? Yes, it does. I'm just going to mark this, yes. Can you discuss more on what it means to have the right embedding algorithm? How can you evaluate that you use the right embedding algorithm? This is going to be a pretty complex question. I think this is something that you should ask either on the recording in a commentary or on LinkedIn. Is there a reference architecture for setting up this kind of system, a test system to examine and consider duplicating? Atin?
Can you quickly repeat that?
Is there a reference architecture for setting up this kind of, I think this kind of system that the question is referring to is about like the RAG plus the eval stuff. And so he was asking, is there a reference architecture for it and a test system for examining and consider duplicating?
Yeah, these are, it's not commoditized yet. It's all work in progress for now. But yeah, if you hit me up offline, I'm happy to share some new, white papers and blogs that have been written in the industry, including from us as a reference.
Okay. Yes. Thank you, Atin. Thank you guys, everyone, for coming. We are at time. And I'm a very time conscious person, so I'm going to cut this off. If you have any questions, please do not hesitate to reach out. We will be posting this online. You can find us on LinkedIn. Please ask any questions that you may have. Thank you guys all for coming, and I'll see you guys next time.
Thank you.